Okay. So now here, firstly we assume let f of x1, x2 equal to this. Okay. Since we have an inequality over here, we'll be solving it using a Tucker, sound like conductor method. Nice. So now for this, firstly we need to define a Lagrangian function. Defining Lagrangian function. So that is basically x1, x2 and lambda 1, because we have one constraint. For the constraint we can write it as this: let h1 is equal to 2x1 plus 5x2 minus 98 equal to 0, or no need to write equal to 0, just this much. Okay, and now this becomes f of x1 x2 minus lambda 1 h1. Now if we substitute, we get 12x1 x2 plus 2x1 square minus 7x2 square minus lambda 1 into 2x1 plus 5x2 minus 98. Nice. So now what now? Oh yeah, now we use our Tucker conditions. Now we use Tucker conditions. So we get h1 should be less than equal to 0, basically a constraint. Then our del L by del x1 should be equal to 0, del L by del x2 should be equal to 0, and also x1 x2 should be greater than equal to 0, and lambda 1 should be greater than equal to 0 for maximization. And lastly, but the most important one, lambda 1 h1 should be equal to 0. Now del L by del x1 can be calculated easily, and we get it as 12x2 plus 4x1 minus 2 lambda 1 equal to 0. Then we get del L by del x2 as 12x1 minus 14x2 minus 5 lambda 1 equal to 0. Okay, now this is 1, this is 2. Woohoo. Then we have h1. Okay, that is basically 2x1 plus 5x2 minus 98 should be less than equal to 0, which is our condition 3. Now we can finally move on to lambda 1 h1, which is equal to lambda 1 into 2x1 plus 5x2 minus 98 equal to 0. Now we take case 1. Okay, case 1 we assume lambda 1 equal to 0. On assuming lambda 1 equal to 0, we get two equations from 1 and 2. From 1 we get 12x2 plus 4x1 equal to 0. We'll call it 1 dash. And from 2 we get 12x1 minus 14x2 equal to 0. We'll call it 2 dash. Okay, now I'll be using my calci to solve these both simultaneously. Two equations and two unknowns. This is x1. Minus 14, 0. See, these are the two equations. Here there's 4x1 here, but 4 comes first because x1, x1, x2, x2, that's it. And on solving we get x as 0 and y as 0. So you get x0 as 0, 0. Okay. So is this a valid solution? That is what we need to check. So now h1, this dude here. So in this dude, if we substitute our point 0, 0, okay, we'll see that we'll get 0, 0, minus 98 less than equal to 0. So minus 98 less than equal to 0, which is true, no? So x0, 0, 0 is a valid point. Now let's consider our second case, okay? Case number 2. In case number 2, we assume that our h1 is equal to 0. That is 2x1 plus 5x2 minus 98 equal to 0. Okay, so this is one equation, and the other two equations we can call this a. Okay, and the other two equations are just equation 1 and 2. Okay, so we solve equation 1, equation 2 and a simultaneously. Okay, so now we'll have three variables. Okay, equation 1 is 4, 12 minus 2, 4, 12 minus 2 and 0. Then we have 12 minus 14 minus 5, 12 minus 14 minus 5 equal to 0. And lastly, we have our current equation where lambda 1 is ka coefficient is 0, that is 2 plus 5 minus 90. This is lambda 1 ka coefficient 0, and minus 98 when it goes to the other side becomes plus 98. On solving, we get x is equal to 44 and y is equal to 2. And our lambda 1 ka value is 100. Okay. So now we got another stationary point. Let's call it x0 dash 44 comma 2. Now our first stationary point was x0 is 0 comma 0 and the other one is 44 comma 2. Now in order to just check which one is valid, means like both are equally valid, I think we can substitute this in equation number 3 to check. Okay, equation number 3 was this: 2x1 plus 5x2 minus 98 less than equal to 0. So 2 into x1. Okay, so we get 88 plus 10 minus 98 less than equal to 0. Is this true? We get 98 minus 98 less than equal to 0. So even this point is valid. Yeah. So now how do we differentiate? So now the only way to differentiate is we substitute both the points one by one into a function. Okay, and then we look at the question. In the question we were told to maximize our function. So at whichever point we get the maximum value, that is what we would take. If we put 0 comma 0 in this function, 0 0 0, we get entire value as 0. Okay, I don't think that's maximum in any way, but could be also. There's only one way to check, by substituting the other point, that is 44 comma 2 in this. So we substitute it here. 44 square minus 7 into 2 square, we get 4900, which is leaps and bounds above 0. So definitely this is the point that we need to consider. Therefore, as x0 dash gives greater value than x0, x0 dash is our point of maxima, and the maximum value of a function is this 4900 respectively. Yeah.